Here we'll do another graphing problem for this polynomial x to the fifth minus 16x. Before we begin graphing, we'll find the factored form for this. To begin factoring, we'll first look at what each term has in common. We might notice that both terms contain an x, so our first move will be to factor out x. If we factor out x from this expression, we'll take each term and divide it by x. We'll take x to the fifth divided by x, remembering the invisible 1 on that x. X to the fifth divided by x to the first will give us x to the 5 minus 1, which is x to the fourth. We'll do the same process for the negative 16x and divide by x. Here the x will cancel out. This gives us negative 16 for the other term. After factoring out x, we now have x to the fourth minus 16 inside the parentheses. Now inside the parentheses, we may notice we have x to the fourth minus 16 as a difference of squares. When you have a difference of squares, we take the square root of the first term. That's the same as saying x to the fourth square rooted, or x to the fourth raised to the 1/2 power if you wish. That's the same thing. If we operate that square root on x to the fourth, we get half of that power, which is x squared. We also take the square root of 16. The square root of 16 is 4. And so now, because of our difference of squares, we'll have two parentheses where that difference of squares once was. The terms will be x squared and 4 in both parentheses, and one will have a plus and one will have a minus. Now, you may also notice that we have another difference of squares, x squared minus 4. Now we take the root of x squared and the root of 4. The root of x squared is the same as saying x squared raised to the 1/2. This will just give us x to the first power. We'll write the invisible 1 on there as well. The square root of 4 is just 2. So where this difference of squares, x squared minus 4, once was, we'll now have two additional parentheses. We begin by writing the x we already had, and write the x squared plus 4 that we already had. And then in the other two parentheses, we will have x plus 2 and x minus 2. Let's examine this again to see if we can factor anything else out. All of the terms right now are linear except for one. We have x plus 2, x minus 2, and x in front. The only term that is still x squared or irreducible quadratic is x squared plus 4. There's no way we can factor a sum of squares, therefore we have to stop and say the x squared plus 4 is irreducible. Therefore our factored form is x times x squared plus 4 times x plus 2 times x minus 2. Now we'll set out to deal with the x squared plus 4 and change that into complex terms. Part B asks us to get complex linear terms for this now factored polynomial. Our only irreducible term is the x squared plus 4. In order to get the complex terms, we'll need to use the quadratic formula. The quadratic formula says we'll find x equals negative b plus or minus root of b squared minus 4 times a times c, all divided by 2a. In our irreducible quadratic term, we have x squared plus 4, meaning our a is 1, our b is 0 because there is no x term, and then our c is positive 4. We'll now place those numbers into the quadratic formula. We'll end up with 0 plus or minus root of 0 minus 4 times 1 times 4, all divided by 2 times 1, which is 2. Now we simplify the terms inside of the root. Negative 4 times 1 times 4 will give negative 16. Therefore, we now have plus or minus root of negative 16 divided by 2. Now let's try to simplify that root of negative 16. If we have negative 16, we can change that into 16 multiplied by negative 1. Then if we take the root of 16, we will get 4. And if we take the root of negative 1, we'll get I. Anytime you have root of negative 1, we'll use the letter I to represent that. This will give us plus or minus 4i divided by 2 If we divide, we'll get plus or minus 2i. This means that x can either equal 2i or x could equal negative 2i. Now that we have our solutions, the only thing we need to do is set them equal to 0. In order to set the first solution equal to 0, we'll need to get 0 on the right, so we'll subtract 2i from both sides. When we subtract 2i, we'll have x minus 2i on the left and 0 on the right. For our second solution, we will instead add 2i because this will again give us 0 on the right. This will give us x plus 2i on the left equals 0. These two new linear terms will go in place of our irreducible quadratic. So where the irreducible quadratic once was, we'll place two new parentheses. The x that was in front stays there, the x plus 2 also stays, and the x minus 2 also stays. In our new parentheses, we'll write x minus 2i and x plus 2i. This will be our factored form with complex coefficients. With our newly factored form, let's get more information about this polynomial. For parts C and D, we'll look for the intercepts and the end behavior. We'll begin with the y-intercept. For the y-intercept, we'll let x equal 0 and see what this function gives us. If we plug 0 in for each x, notice that we have 5 places to plug it in. We'll end up with 0 times 0 minus 2i times 0 plus 2i times 0 plus 2 times 0 minus 2. However, since we have a 0 on the outside, it doesn't matter what the rest of the multiplication chain gives us. 0 times any of these is still 0. This means that our y-intercept is 0, 0. Let's also look at our x-intercepts. For our x-intercept, we'll set each piece equal to 0 and look at what solution that gives us. Our first piece is just a lone x. We'll set that equal to 0. Our next pieces are imaginary pieces, x minus 2i and x plus 2i. Then we'll have x plus 2 equals 0 and x minus 2 equals 0. Our first piece says x equals 0. Since this already equals 0, we don't need to do anything to it. We'll just let x become 0, and y will also be 0. Therefore, our first x-intercept is 0, 0. Because our y-intercept also said 0, 0, we already knew this. Anytime you have 0, 0, that is both an x-intercept and a y-intercept. Our next pieces are imaginary, x minus 2i and x plus 2i. Anytime you have an imaginary answer, this will not show up on the graph as an x-intercept. Therefore, because these two are imaginary, we can say that this x-intercept does not exist. We'll now say D and E for both. However, the other two pieces will give us real solutions. If we have x plus 2 equals 0, we'll just subtract 2 from both sides and get x equals negative 2. If we have x minus 2, we'll now add 2 to both sides, giving us x equals 2. Therefore, our next x-intercept is negative 2, 0, and our final x-intercept is 2, 0. So we have 3 real x-intercepts, and the 2 imaginary pieces do not give you an x-intercept. Finally, we'll look at the end behavior for part D. We ask ourselves if the highest order term of the function was even or odd. Because originally this function was x to the 5th power, we know this function must be odd, since 5th power is an odd number. This means that in our end behavior, the arrows on either side of the graph must point different directions. Then we look at our leading coefficient and see if that leading coefficient is positive or negative. On our x to the fifth term, we have no coefficient, therefore we place the invisible 1. Therefore our leading coefficient is positive 1, and we'll have a positive leading coefficient. If you have a positive leading coefficient with an odd-powered function, that means our graph will be increasing. When I say that it's increasing, that means we'll have negative infinity on the left and positive infinity on the right. Our graph should be going upward as we go from left to right. Now that we have our intercepts and our end behavior, let's graph the function. Here I've marked down all of the intercepts on the graph. Before we actually draw the graph, let's look at the multiplicity of each of the zeros. The first term was the x. That gave us x equals 0. Since this x is raised to the first power because there's no exponent written, we'll say that's a first power term and it should cross straight through. The imaginary terms will not appear on this graph at the intercepts. We'll skip those. We'll move on to x plus 2. X plus 2 gave us this 0, x equals negative 2. This also has no exponent, therefore it's first power, and it should cross straight through also. Our final term was x minus 2, and that gave us our final x-intercept at x equals 2. That is also first power, and it should cross straight through. Therefore, as we draw the graph, we'll cross straight through our intercepts. Now we'll look to our end behavior and we'll place arrows on the graph to represent those. We'll have negative infinity on the left, which means we'll have a down arrow on the left side. We have positive infinity on the right, so we'll have an up arrow on the right side. Now we'll start from our left arrow and work our way left to right, making sure to cross through each of these x-intercepts. Starting from the arrow, we'll cross through that negative 2. Make sure we turn around and hit that 0. We'll continue downward, but we'll have to turn around again and cross through x equals 2 and hit that up arrow. And now our polynomial graph is completed. We now have a sketch for the polynomial x to the fifth minus 16x.